Greetings and welcome, friends. Mr. Waddy here today. It's a big day today. We are talking about exponential functions. We are in section 6.3, and well, let me just tell you this. An exponential function is a nonlinear function of the form y equals a times b to the x. So that variable is in the exponent, right? It says where a cannot equal 0, b cannot equal 1, and b is greater than 0. Lots of weird restrictions on this. We'll talk about those maybe in a future day. It says as the independent variable x changes by a constant amount, all right, so as I increase x by 1s, right, we made a table as a class earlier, and the x's were increasing by 1s. It says the dependent variable y is multiplied by a constant factor. So instead of being like up 1 over 1, up 1 over 1 of a linear function, this is going to be like multiply by 2 over 1, multiply by 2 over 1, multiply by 2 over 1, a constant factor, which means consecutive y values form a constant ratio. So instead of a slope, we're going to see that y values just get, there's a ratio between them, where it's being multiplied by a consistent factor. So let's first talk about whether or not I can identify linear functions. So let's do example 1 together. We'll see how far we get today. We shall see. It says, does each table represent a linear or an exponential function? Explain. Explain. So here we go. We see that the x values are, what are these x values doing?
Increasing by 1.
Yeah, those are just plus 1, plus 1, plus 1. Let's see, 2 to 4, that could be plus 2, or that could be times 2. Let's see which one happens. So to go from 4 to 6, what happens? Is it plus 2 or times 2?
Well,
to go,
plus 2.
Yeah, it's just plus 2. Yeah, so this one didn't work. And then to 6 to 8, that's plus 2. So because these are pluses, this is a linear function, linear. Okay? Right? Those have a constant rate of change, where our exponential functions have a constant factor.
Just say rock.
Let's see, plus 1, plus 1, plus 1. And what are these ones doing? 4 to 8, it could be plus 4. Or, what's another possible pattern? It could be times 2. Let's see which pattern is consistent. 8 to 16, does plus 4 work?
No.
No.
Times 2, times 2. So that's
It's times 2. And 16 times 2 is 32. So it's not that one. This one is exponential. Right? Exponential. Exponential. Excellent. So that's one of the ways you can recognize exponential functions. Also, they said that exponential functions are of the form y equals a times b to the x. When you have a variable in an exponent, right? It will be an exponential function. So the variable is in the exponent, is what we're seeing. Okay, let's do this one. Example 2, evaluating exponential functions. So this is going to require us to recall the idea of PEMDAS, right? Order of operations. Question, comment? Yes. Yes, you may. So PEMDAS, right? Parentheses, exponents, multiplication, division, and then addition, subtraction. So exponents happen first. So they say, evaluate each function for the given value of x. So what they're going to have us do is, if x equals 3, they're saying, hey, plug 3 in for x and let us know what y equals while you're at it. So y equals negative 2 times 5 to the 3rd power. Okay, let's figure out what this is. Negative 2 times 5 to the 3rd. I do not do the multiplication first, because PEMDAS would say, hey, let's do some multiplicado first. All right. Sorry, exponents first. My bad. Exponents, not multiplicado. There we go. So we've got negative 2 times, what is 5 to the 3rd power? That means, don't write this down, 5 times 5 times 5. Okay? I'm going to simplify this in a second. 5 times 5 is 25, and 25 times 5 is 125. All right, 125. Okay? So 125 is what you get. And now I'm going to multiply that by -2, and I believe that's going to be -250. So that means when x was 3, y was -250, right? So it's just order of operations, PEMDAS. In case you're wondering how to, do this on a calculadora. All right, if I want to, first of all, I got to turn the calculator on. If I want to do exponents in this, let's see, what was the exponent we just did? We did 5 cubed, 5 to the 3rd power. I'm going to hit 5, normal style. And then there's this little button right here. This is called a caret. I don't believe it's spelled like the vegetable carrot. And I hit that. And so 5, that means like 5 to the, and then I'd hit 3 and hit enter. And I get the 125 that I had seen earlier. You also might have a button. So it's either this button, or you might have a button that's a y to the x button, I believe. One of those might work. So you can tinker with those. Just make sure, whatever calculator you might have, that 5 to the 3rd is 125. All right, let's try this one over here real quick. So plug in -2 for x. So y equals 3 times 0.5 to the -2nd. Now that's weird. What does it mean to multiply 0.5 by itself -2 times? That's weird. Let's hit a calculator for this. There are some properties of exponents that, if you are aware of those, might help you out. So I'm going to do 0.5 to the, and I'm going to just be careful. I'm going to put the -2 in parentheses like so. And when I did negative, that negative sign, all right, highlighted right there, that negative sign, that is not a subtraction symbol. All right, your calculator, this is a negative sign. This is the subtraction operation. Okay, so you got to use the negative symbol. And I hit enter. That is weird. It's just 4.5 to the -2 is 4. Wow, you guys maybe should do some experimentation with that at some point. So that's the same as 3 times 4, and then 3 times 4 is 12. So that means for this function, I'd have when x was -2, y was 12. Right? So as far as evaluating those, it's not that bad. It is not that bad. That's not that much cheese. So, all right, here is another example that I gave you guys. We made a table. We did something similar to this a moment ago. And so graphing, if I want to graph an exponential function, making a table of values works, right? That's usually our initial interaction with something, is making a table of values. And then I can plot points and I can draw the line, curve, whatever. Okay, let me start by plugging in 1. So 2 to the 1st is 2, okay? All right, if I plug in 2 for x here, 2 to the 2nd is 2 times 2, which is 4. Okay, so the output is 4. 2 to the 3rd is 8. 2 times 2 times 2 is 8, yep. Or just look at it as 2 cubed is the same as 2 squared multiplied by another 2. All right, and 2 to the 4th, what's 8 times 2? 16. All right, so, or 2 to the 4th just means 2 times 2 times 2 times 2, right? Multiply 4 2's together. And so I get 16. Now, according to this pattern, each of these are doubling, right? There's a...
So these are 2 to the 0.
And to move backwards,
Oh, it's going to be 1.
right, if I was moving backwards, that's dividing by 2. Dividing by 2. Dividing by 2, right? So 8 divided by 2 is 4. 4 divided by 2 is 2. What's 2 divided by 2?
1.
1. According to the pattern, this is 1. But let's see, what is that according to the formula? I'm claiming, this is weird, that 2 to the 0 is 1. Right? According to the pattern, we're saying it's got to be 1. But don't you agree that this looks really weird?
Yeah.
That looks weird. That looks really weird, but that is in fact the case. The pattern applies. Let me do 2 raised to the 0th power. I get 1. You know what's even crazier? Let's do 5 to the 0. 1. Let's do that number to the 0. 1. That's weird.
0.5 and 0.25.
Anything you raise to the 0 is going to equal 1. All right.
Wait, it's going to be actually more than that. That's fine.
Well, let's divide by 2 again. What is 1 divided by 2?
0.5.
0.5. Let's work with fractions. In this case, we'll call it a half. What's half of a half?
Quarter.
A quarter. All right.
This number that I just wrote out, I don't even know what it is, equals 1. It's 5, 6, 6, 2, 4, 5.
That doesn't seem right.
6, 1, 6, 5, 6.
4,
6, 4.
So you plugged in a super big number
Yeah, 4.
and raised it to the 0? Here, we don't have time for it, Austin, to hear the whole thing.
6,
What did you get, though?
6.
All right. We'll do an Austin check-in like in 5 minutes.
7,
He plugged in a really big number to the 0th power.
1.
Now, guys, what I want to point out is when I plug in a negative exponent, I get a fraction
That big number
output.
1.
That seems wrong.
That big number
Because
is 1.
it's basically timesing it by a negative, so shouldn't that be a -1?
It's not multiplying it by a negative, though.
It's divided.
It's raising it to a negative exponent. All right, which is weird, but the pattern is divide by 2, divide by 2. Let's plot some of these points on my graph. So 1 was at 2.
Because when you're having it in like the power of like squared, when you have it squared, you're not multiplying it by any other number.
Let's see. 0 here we don't have a lot of time, so we'll spend probably 2 more days on this. But I plug in 0, I get 1. I plug in 2, I get 1, I got 2, so 1 comma 2. When I plugged in 2, I got 4. When I plugged in 3, what did I get?
8, 16.
8. Okay? And notice the heights of these points. 1, I doubled the height and moved over 1. I had 2, I then doubled the height and moved over 1. I had 4, I doubled the height and moved over 1. I can't even fit 16. Now to go backwards, to go less than 1, I'm halving the height and moving backwards 1. So I was at a half. Half of a half is a quarter, so half the height and move backwards 1. Half of a quarter is an eighth, half the height and move backwards 1. And it's getting super close to 0, but it's never going to get there.
1.
Let me see if I can draw this curve. No, these curves are so hard to draw. It's something kind of like that. So try to connect your dots as best you can. Let's see, I was trying to use the guide tool to have a less wobbly hand. I missed the last point. So in this direction, it's going off to positive infinity. In this direction, and then that was the question that we were discussing as a class earlier, does it ever get negative? No. No, because repeated division by 2 isn't going to make this negative. Does it ever hit 0?
No.
No. It gets infinitely close to 0.
Close to 0.
Which we call, those numbers are infinitesimals. They're super small. And then imagine even smaller than that. And even smaller than that. But graphing using a table of values, this is what we see. And we see that it doubles in height every 1 unit that I move over. And so these are kind of interesting to graph. A little bit interesting. Now, it turns out I can... let's see. Actually, I've got a... Let's see, I'm gonna show this. This is as far as we'll get today. Hopefully example 3. Alright, we're gonna spend a few days on this, because this is like a completely new and bizarre function world for us. It turns out I can try different values of my base. Alright? When my base is bigger than 1, it grows as I move to the right. Let me show you. I've got a little hyperlink that I'm going to open up here. And here we go. So I've got these sliders. Okay. If I make my b value bigger than 1, it grows as it goes to the right, right? It's getting bigger and bigger to the right I go. Mario runs uphill, a hill that is getting steeper and steeper, faster and faster. If I make b less than 1, actually at 1 exactly, it's a horizontal line.
Yeah.
But what's going to happen when b is less than 1?
It's going to be
It actually gets smaller and smaller.
closer to 0, not 0.
Yeah, that's weird. So when I do repeated multiplication by a number less than 1, like 0.6 or 0.5, right? I can't, oh, I know how to do it. Bam, done. It's going to get smaller and smaller, right? Half the height, move over 1. Half the height, move over 1. Half the height, move over 1. Actually, I was counting by 2s there, I just realized. But when b is less than 1, here, let's go back to our graph. Notice that when b is less than 1, but bigger than 0, it goes down to the right. But what about when a is positive or negative? Let's go back to our graph. Let's make b back to like 2 or something. Oh dear, what did I just do? There we go. There we go. All right. What happens when I increase a?
it comes closer.
Now what does it appear to be doing? It looks like it's stretching it.
Increasing and then it's making
Yeah, can I do one of these? Let's see, let's make it, it's a vertical stretch. A vertical stretch. All right. What happens when, so just like when we did absolute values back in the day, multiplying by an a bigger than 1 was a vertical stretch. Notice when a is 2, that it actually doubled the height. It made the heights of these even higher. When a is 3, it tripled the height. This used to be 1, now it's 3. This used to be 2, and, wait a minute, 2 to the third, or sorry, man, I'm messed up because I'm looking at the wrong point. This used to be 2, but now 2 times 3 is 6. When I plugged in 2, I used to have 4, but now 4 times 3 is 12, right? So yeah, the a value makes it grow faster. It's a vertical stretch. And when a is negative, you already saw some of those results, it actually flips it upside down. All right, it flips it upside down, which is kind of weird, right? Kind of weird. What was the other one that we saw? Yeah, so when a is negative, it flips it upside down, whichever way it goes. When b is greater than 1, it grows to the right. When b is less than 1, it shrinks to the right. So let's see. Let's do this one example, example 3, last one. Right, so these are weird. It's going to take us a while to get used to it, and that's okay. All right, that's just a-okay. All right, so I gave you guys a parent graph here. Okay, so you guys got this graph as well. This is currently the graph of 2 to the x. All right, so I'll write it in the same color. Y equals 2 to the x is this graph. All right, if I multiply this by 4 on the outside, that's going to give me a new graph. And what it's going to do is take all of these points, right? So here was 1 high, here's 2 high, here's 4 high, here's 8 high. It's going to take all of these points, here's a half high. And what does multiplying by 4 do? It's going to multiply those y values by 4. So what is 1 times 4? 4. What is 2 times 4? 8. So plot that point up there. What is 4 times 4?
Very good.
4 times 4? 16. And then here, 8 times 4, that's going to be the 32, but that's way off my graph. I can't fit it. I'd have to like scroll up here to get it. It's like there or something. I don't know. And how about this? What is a half times 4? 4 times a half, or 4 divided by 2? 4 divided by 2?
Oh, it's 1/8.
No, 4 divided by 2. Or 4 times a half?
4 times a half.
What's half of 4?
No, it's 2.
2. There we go. All right. And so all of these values just got quadrupled in height. And then I'll try to draw the best curve I can. And so multiplying by an a value just increases the y value by that factor. So it's a vertical stretch by 4, by a factor of 4. All right, so all of our old transformation skills are still going to apply. All right, that's the idea. So we're gonna do more of this over the next 2 lessons. So thanks for watching, Internet friends. Have a great day.